today we'll try and make the link between the information that we need to be able to solve problems of flow in pipes with our initial foray into dimensional analysis. Dimensional analysis, the oxymoronic or the misnomer. Maybe it should be dimensionless analysis because that's what we're using. You'll recall that when we talked about dimensional analysis, let's make it full screen so you can do that. Yeah, okay. You'll recall that when we did this, if I can just draw up here, a lot of the calculations we did, we had done in terms of where we were talking about the forces that were applied on a wing, or the forces that were applied on a satellite dish, for instance. Then typically what we did was we looked at figures that allowed us to evaluate two important dimensionless numbers which describe those behaviors. And depending on the particular geometry we had, we tried to look at Reynolds number similitude, if you like, kinematic similitude. And if that was the case, then that gave us dynamic similitude. So this was what we called kinematic similitude. So we wanted the geometries to be the right geometries. If we had that, then we wanted kinematic similitude, which meant that the Reynolds numbers for the prototype, the model, which would be the method by which we'd get this curve from the model results. For our prototype results, we wanted to use the right Reynolds number, and if we had the right Reynolds number, we'd presume that the Euler number we got for that was the correct one for that prototype. And if we knew what the other components of the Euler number were, then such as velocity and density of the fluid, then we could make the connection between the magnitude of the pressure that was applied on this and therefore the force. And so when we deal with pipe flow, we'll do similar things. And we can actually make the connection between these dimensionless analyses and what we'll try and do for pipe flow. So the first thing we need to do is think about what we'd like to be able to solve. And so we've kind of done this in the past. And so if you imagine a pipe flow network is looking something like, I don't know what it would look like. Kind of convoluted, but that's basically the idea. Then what we do know is that we can write Bernoulli's equation for that. And Bernoulli's equation for that is just the energy equation. And it says something like, if we have an upstream location and we have a downstream location, and the flow velocity through the system is exactly as we write here, then we can write Bernoulli's expression as elevation, pressure head, elevation head, velocity head. You remember we had this alpha number which would vary between 0 and 1. If we're writing it from upstream to downstream, we had a pump head that was in there. And that had to equal the magnitudes of these Bernoulli terms at the downstream location. Elevation, velocity, and two additional terms. So the sum of head losses, we'll divide them into two terms. One is we'll call major, and the sum of head losses minor, min. Like. And so those are the behaviors that we want to deal with. So you all remember this, of course. This is the pressure head, elevation head, velocity head. This alpha value is between 0 and 1. Just to remind us, 0 and 1. And if the flow coming out of the pipe is uniform, then it's equal to 1. If it's not uniform, then it's less than 1, but we don't really worry too much about that. It's not a substantial component. We know that the pump head is equal, if we want to convert it into useful properties, it's the power of the pump in terms of watts divided by the mass flow rate times gravity. So we've certainly dealt with that before. So that's this parameter here. And so we've defined all of the terms here except for these other two terms. And so what the essence of pipe flow is to be able to figure out exactly what the magnitudes of these losses are. And so, surprisingly maybe, I've drawn this specifically with bends in it. And so the minor losses are typically the losses that occur in going around a corner. So we know that when we certainly we know that if we have a fluid velocity in this pipe here, then the magnitude of the velocity in both legs of this pipe will be the same. And so that won't have changed. But since velocity really is a vectoral quantity that has both direction and magnitude, its direction has changed. So we've had to accelerate it to get it around this corner. And so by accelerating it, presumably we are using up energy to be able to change it from one state to the other. And so we get minor losses related to that. And we've already actually seen them before. And so we know that minor losses are typically represented by some loss coefficient. I think we did this in conservation of momentum, multiplied by the velocity head term, v squared over 2g, which is defined the velocity in the pipe. So scalar magnitude of velocity in the pipe as you go around this bend. And so we won't derive that, but we'll take that as trust. All it's saying is that we can scale the magnitude of this loss relative to the velocity head term. And it makes sense that it should scale relative to this term because that's the reason for the head loss. The head loss is that we're changing direction. We're not changing velocity. We're not changing the speed, I guess, but we are changing the velocity. And so it should scale proportionately to v squared over 2g. And so depending on the particular geometry of the bend, whether it's a 90-degree bend or a 60-degree bend, whether it has flutes in it, whether it constricts, we should be able to figure out the magnitude of this loss coefficient, I guess is the basic idea. So those are the minor losses. The major losses, surprisingly, are the ones that just occur due to straight flow in the pipe. And so the major losses, and I say surprisingly because, nothing's really changing, right? It's just happily going along this pipe, and nothing particular is changing to either the direction of it or the magnitude of the velocity. But the reason for the major losses are that the pipe length is typically very long, and so a small loss per unit length accumulates over the length of the pipe and actually is typically larger than the minor losses that occur within these fittings. Even though the losses in the fittings might be larger, there are fewer of them. So that's basically the reason for that, the nomenclature that's related to that. And so the punchline for this, which we'll visit, is that the major losses fall into two categories. Well, actually, no. They're always equal to something that looks like a coefficient, a length to diameter of the pipe. And so if we're looking at our geometry of a particular pipe, then it has some length. It has some diameter. As we drew last time, it has some roughness. And so if you were to take out this little view here, this would be the size of the pipe. And this magnitude here would be roughness, which in your book is called epsilon. There would be a flow velocity in the pipe. There would be, what else? There'd be a pressure upstream and a pressure downstream. and the change in pressure would be the difference between those two. And so the losses in the pipe are typically given by this expression. A friction factor, squiggly f, length to diameter of the pipe, and also the magnitude of the velocity head term. Bless you. And so I guess this is always true, but it differs for laminar flow. If you remember the movie we looked at last time, Lam in R. Laminar, and the magnitude of the friction factor is equal to 64 divided by the Reynolds number, where the Reynolds number, well, let's do that later. So it's always this magnitude for a circular section pipe. When it's laminar flow, where roughness doesn't come into account, it's always equal to this magnitude. And if it's turbulent flow, then the friction factor is a function of Reynolds number and relative roughness, roughness over diameter, because that's the characteristic. You could scale it with length, but it doesn't seem to make so much sense to make it scale with length. So what you see is that this amount of head loss, it scales directly with the length of the pipe, which you'd expect, right? You double the pipe length, you'd expect to have double the friction resisting flow, and therefore you'd have to double that into here. So when we solve this equation, which we won't do today, what we'll look at today is why these terms are exactly the way they are, and to figure out exactly what they are for both laminar and turbulent cases. And, well, I guess that's basically what we'll attempt to do. So that's kind of the punchline. So we haven't really done anything to get to that punchline, but we've defined what these properties are. So we use Bernoulli's equation. We use it with these pump terms and the head loss terms included in it. We've given the game away in that we know exactly what this pump head is in terms of mass flow rate, gravity, and the watts, the powers that are used. And we've also suggested that the losses divide between minor losses and major losses, minor for the fittings, major for along the lengths of the pipe, and that the major losses are major because they're larger, and typically because there's long length of pipes involved, and that they scale. This equation is always true. It's just that the magnitude of this friction factor changes depending on whether we have this nice smooth flow, which I guess we had last time. I'm not sure. We did have it last time, right? If I look at this, I think we have it. Is it this one? I think it was, right? We had this last time. So see if this comes up. And so it's during this transition from laminar to turbulent flow that we talked about. I don't want this over the top. But this was just flow in an acrylic pipe, presumably quite smooth walled. But as you increase the flow velocity, which is what's happening in this, is you start getting, instead of this uniform, nice single pencil line bead along the length of it, you get this warbling in it. And this is just in the center of it. You can imagine if this is the case in the center, if you move the location of the die tracer close to the sides, you'd also see these warbles. And it's a result of the flow being on average from left to right, but also if you look locally at the flow, you'd see these little vortices and eddies occurring, which are this reverse flow, which make the flow less efficient. And so what we might think, just from looking at experimental results, is that you might expect that this friction factor would change from this regime where you have laminar flow to the case where you have turbulent flow. And so you can basically, and this is, you can see these little loops occurring now. No longer is it just a wave, but now they're actually turning backwards on themselves as you increase it. And ultimately, as you have larger velocities, you start seeing this line spread out because it's actually mixing much more efficiently during the center part of the flow down the pipe. And so you might expect that the flow regime is changing at these different velocities, and the number that we've used to scale velocities in a non-dimensional sense is this Reynolds number. And so you'd expect the behavior would change in some respect with Reynolds number. So let's think a little bit about that. And let's go back to what we've talked about in terms of dimensional analysis to be able to figure out exactly what that would be. And so what I'd like to, so this is what we've done now. So we didn't really get there last time, but now we've talked about why the Bernoulli equation and the energy, which is really the energy equation, if you add in these terms for input into the system or export or dissipation of energy in the system, which are these losses. And so now let's figure out exactly why the magnitude of those losses might be written by these terms. Can we rationalize what this might look like? So there's two ways we can do it. The first way is just dimensional analysis. And so what we could do is we could write our Buckingham Pi kind of analysis. So our Buckingham Pi analysis is just one that takes care of defining all the variables that control our system. And so first of all, we should note maybe that the pressure change between the ends is kind of, we could also think about this as equal to, what would it be? It's equal to a head loss multiplied by a unit weight, right? So all I'm doing is I'm suggesting that, probably easier to write the other way, if we write P over delta P over gamma, that has to be in units of head loss. And so just by rearranging this, we know that the pressure drop between the upstream and downstream is indicative. If we measured that pressure drop, it would be indicative of the loss that we'd have in the pipe, right? So we could measure that. And so let's not work in terms of head losses, but let's just look at what the pressure drop we'd have to physically push fluid along our pipe would be. So in terms of dimensional analysis, we could write it in terms of all the variables that would define our system. And so, okay, I won't use squiggly f because we've used it up here. So a function of, what are the variables that describe our system? Well, we have a velocity of fluid that's moving along our system. We have fluid properties, I guess, which would be density and viscosity. So we have density and viscosity. And we think that we have some length dimensions, or some units that describe the geometry. And those length dimensions, or those dimensions would be the length of pipe that we have. Presumably if we have a longer pipe, we'd have a bigger head loss. Double the pipe, intrinsically you might think that we'd have a double the head loss for the same velocity. We have a diameter of the pipe, and we have this other property, which is the roughness. And so we think that those are the properties that define our system. What are our pi groups? So we have a total number of variables, 1, 2, 3, 4, 5, 6, 7. We have mass, length, and time represented. We have a velocity, which is length over time. And we have density, which is mass over volume. So we have, in these two properties, we have at least all of mass, length, and time represented. And so from this, we know that the number of pi groups we're going to have are going to be 4. So we could use Buckingham Pi to be able to figure that out. Alternatively, rather than using Buckingham Pi, we could also remember that often when we dealt with this kind of system, with these kinds of variables, we ended up with some very specific, important non-dimensional numbers which defined our system. And so what we could do is we could use that to be able to say something about our behavior. And so what we could do is we could just go back and be able to just use these. Let's assume that Reynolds number and Euler numbers are the correct ones. And so if we did that, we could write this just using those. So let's use it. Let's assume, just because it's easier, that RE and EU are our important non-dimensional parameters. And we can do that now in hindsight. People working in the 1700s didn't perhaps have that luxury. They did some experiments and they saw what went on. So what would guide us to think that these would be the appropriate ones? Well, Reynolds number is kind of important, right? Because we've said that what Reynolds number does is it conditions the flow regime that we have. And so if we think that we're using our glass tube and we think that the behavior, we want Reynolds number similitude to be able to calculate the Euler number, then we know that as you change the Reynolds number in pipes, there is some significant change in the flow regime, and so that might be an important indicator that we have to look for in terms of similitude. So why Euler number? Well, the reason for Euler number is that we also know, I'm going to just stop that, I guess there's no noise coming through. For Euler number, we know that the forces on structures, in other words, the change in pressure from going upstream to downstream, also changes, is indexed with the Euler number. And so we used it for the calculations with wings. We used it for the calculation with flow impacting on a satellite dish. It's really not very different to have flow occurring in here. It's just that in here, the flow going along here, you'd imagine, has some shear stresses acting against it, and it's that which dissipates the loading that goes through there. And so we think that Reynolds number and Euler number are going to be important variables just by inspection. We know that Euler number includes something which is a change in pressure, a density, and a velocity squared term. And we know that Reynolds number is given by a velocity, a density, a length term, a characteristic length term, and a viscosity. And so we know that there's an extra term in here which represents length, not Q, it's just a length term. And so in this particular case, we have three length terms, right? We have length of the pipe, diameter, and the roughness. We could use any single one of those terms because they're all lengths. It turns out that the best one to use, the most characteristic one to use, would be to scale things with the diameter of the pipe, just by experiment. And I'm not sure I can rationalize that particularly, but that would be the magnitude that we typically use for the Reynolds number. And so if we come back to this expression here, we can then take both of these terms, and I'm just going to write Euler number is equal to some function of Reynolds number. And we know that we have four non-dimensional terms, and so we have two other terms to fit in here. And so certainly two other terms that could fit in here that would be non-dimensional if we're just doing them by inspection. You can do it by Buckingham Pi, or you can do it by inspection. We can take length over diameter, and we can take roughness over diameter, or length. Doesn't matter. It's just that I know the answer, and that's why I'm driving it. You could use any combination and do some experiments, and some of them would work out better than others as parameters, which if you chose them, you'd get the same results from experiments as you vary those different parameters, but still use those same groups. And so if you substitute those values into this, then you end up getting, well, basically, delta P over rho V squared is equal to some function of those parameters. So Reynolds number, I guess I'll write it out. Velocity, density, diameter divided by viscosity. This other important one, length over diameter, and roughness over diameter as well. And so in this, if we wanted to, since we know that this is also true, if you wanted to, you could substitute this value for delta P into this, and now you have an expression that gives you head loss in terms of the behavior. So we know that those could possibly be the variables that we would use. And so let's have some validation here for ourselves that we've been very clever, and look at what experimental results might give us. Okay? So we think that there's some loss term that's a function of Reynolds number, length over diameter, and friction factor. So what we're trying to do is we're trying to figure out exactly what this magnitude of this friction factor might be. And we've said there are two particular cases, one where it's laminar and one when it's not laminar, which is turbulent. And so what we can do is we can look at some results that basically show that behavior. And they're in these, okay, they're right here. So this is the this is the idea. So this is what pipe flow all revolves around. This is perhaps the most important chart. This is the only important chart maybe that we'll use when we talk about pipe flow. It's called a Moody chart after its originator. And it all represents the fact that we want to know what the, I don't know if that shows actually, I'll just move it down. We know that the head loss is equal to some, we've surmised that the head loss is equal to some friction factor, length to diameter of the pipe, and the velocity head, phi squared over 2g. And so if we have any pipe that we have in our hand, we can certainly get the length to diameter just by measuring it. If we know what the flow velocity is along it, we have this term as well. And so the only unknown really is this scaling parameter, which says how big the frictional loss, F is for friction, F is for friction factor. And so the magnitude of this friction factor is given here as a function of these parameters. So what we had before, I don't shoot back, we basically said that this is some proxy for this friction factor, and it's a function of Reynolds number, length to diameter, which we know on an individual basis for the pipe, and also on this relative roughness. And so what we'd expect then is that in this diagram we'd have some way of being able to define the friction factor for these two regimes. And we said that for laminar flow, the friction factor is equal to 64 over Reynolds number. And for other flows, non-laminar flows, the friction factor is a function of Reynolds number, but also this relative roughness, epsilon over d. In other words, when this number is 0, it means it's a nice smooth pipe. When this number is bigger than 0, it's getting progressively rougher relative to the diameter. And you see this behavior here. So this would come from running an experiment. So you do an experiment in a pipe, and you do it at a Reynolds number of 10 to the 3. You'd be able to calculate a magnitude of this friction factor, which would be this point. You'd increase the Reynolds number to 4 times 10 to the 3, and you'd get a point here. And you just, if you did intermediate values, you'd get numbers on this straight line. And so that just comes from doing experiments, nothing more than doing experiments. If you then increase the Reynolds number, then what you find is that you get different results. So in other words, if you start off here, and this is kind of undefined area, but if you drastically increase the Reynolds number, and your pipe has a particular roughness. So if you have a smooth pipe, so actually this one. So if you have a very smooth pipe, and you keep on increasing the Reynolds number, then your experimental results will just define a line as you increase the Reynolds number, which will give you this pressure loss. You'd measure the pressure loss, and you'd convert that into this friction factor, right? Remember, what was the expression? The pressure loss that you measure is just equal to the head loss multiplied by the unit weight of the fluid. So if you measure the pressure drop along the length of the pipe, automatically you have this head loss. And if you have the head loss, then we know that the head loss is equal to some friction factor, length over diameter, and v squared over 2g. Right? So you do an experiment in a pipe. You give it a velocity which is equivalent to some Reynolds number. You know how long and how wide your pipe is. You measure what the pressure drop is across the length of the pipe just by knowing this. And the only unknown you have is a friction factor. And so for every experiment you do at every velocity, you measure the pressure drop and you get this friction factor. So you're able to get these points on this graph. And so by using non-dimensional variables, you hope that when you now double the diameter of the pipe, that your results should still be true. That's basically the idea of dimensional analysis. So for the very smoothest pipe, you get these results, and that's one bounding line. If you take a pipe that has a relative roughness of, say, 5/100ths, so this is just, the values of this are just this. So if you have a pipe which is a meter in diameter, and your roughness is 5 centimeters, is that right? Yeah, it'd be 5/100ths. Then this would be the relative roughness. That's actually a lot of roughness when you think about it. And if you did the experiments with this particular roughness, then you'd get, by changing the Reynolds number, you'd end up with a whole bunch of different results, which would give you the value for this particular roughness. And so the idea is now you just work your way through the rest of the roughnesses and you can fill out this whole diagram. Don't need to know anything about solutions for flow in pipes. In fact, you can't get those solutions for flow in pipes from an analytical way. You just do it by experimentation, and then you hope to be able to apply this for all the conditions that you could imagine in terms of relative roughness that you have for different pipes and different flow regimes. So that's it. And so we haven't done anything here other than suggest that we can do some experiments in place. The one thing that is interesting, so this, or interesting to me, I don't know how interesting to you it might be, I think it's quite curious, is that the magnitude of this parameter here turns out to be defined by a very simple formula. And if we wanted to, I suppose we could do that. I don't know whether it's worthwhile or not. It's maybe useful to know where this comes from. We didn't spend much time dealing with at the time, but when we talked about Navier-Stokes equations, which we didn't, it seems like it's not an important thing for us to talk about in this class, because I think it's just beyond this class. But we did talk about flow, if you remember. I think we talked about this very briefly, if you looked at the videos anyway. We talked about flow between a parallel-sided duct. And so it turns out that we have these Navier-Stokes equations, which basically represent the same as Bernoulli equation, but it's a differential statement of what's going on. And we can integrate those differential equations to solve for the flow rate in a parallel-sided duct. If you look in your book, and also here, you can also get the flow rate for flow within a, do we have it? Is that, no, okay, that's fine. Perhaps we don't have it. Yeah, that's for a parallel-sided duct. Okay, I guess we don't have it. All right, I thought it was there. My mistake. So you can imagine that if we zip back to where we were, sorry for the whiplash. If you imagine that we look at, for instance, the flow in a single pipe, just as we've talked about here, then we could, if we wanted to, get a solution that gives us, for instance, the change in pressure as we go from upstream to downstream with some velocity in a smooth pipe where we have laminar flow. And so if we have some length of this pipe, just as we've had before, some diameter of this pipe, as we've defined before, we can actually get the average velocity is a function, I have it written down here, as equal to the diameter squared divided by 32 times the viscosity of the fluid times the pressure change over the length of the pipe and divided by the length of the pipe. And so that's just a solution. This happens to be the average velocity, and it's the average velocity because if you think about what you'd expect the velocity to look like across this pipe, it's actually kind of parabolic. So in the middle of the pipe, where it's furthest away from the edges, where it's kind of anchored to the wall, the velocity would be the largest. Right at the wall, the velocity would be zero because the fluid, if you like, is attached to the wall, just like in our calculations for viscosity. And so what we'd be using in this particular case is we'd be presuming that, Newton's law of viscosity is the shear stress is equal to the viscosity times the change in velocity with radius in this particular case. This is the radial direction. And so we could solve this differential equations which describe flow in here for these particular boundary conditions. Zero velocity attached to the walls to give us a velocity distribution. And if you integrate that distribution to give you an average velocity, then this is the result that you get for the pipe. It turns out that if you do that, I don't know if I really want to do the manipulation. I suppose you could make the connections here is that if you substitute here for the fact that this pressure change is equal to the head loss multiplied by the density and gravity, and you could presumably, well, not presumably, you can manipulate it to be able to get an expression which gives us the head loss is equal to some friction factor multiplied by length over diameter, v squared over 2g. And so if you do that, if you make some substitutions and manipulate this expression with this term in here for head loss, then you find out that what would come out of this is that you'd end up with this friction factor would be 64 over Reynolds number and length over diameter and v squared over 2g. So I won't bother torturing you with that, but you should be able to substitute this value of pressure in here, and you can see already that this 32 is in there and this 64 comes out of it. So there's another 2 that's going to come out of there, and it's just going to come out of the manipulation by substituting some different values. And so merely by taking this solution for laminar flow in a pipe, we end up getting this magnitude for the friction factor, which we called lowercase squiggly f, which is exactly the gradient that we end up of this line here. And so that's exactly where it comes from. So there's no particular magic in that. It just comes out of the very simplest case that we can evaluate behavior for. Nothing more than that. And so the other interesting, well, I think the other notable point in this is that for these behaviors here, it's not possible to get a simple analytical solution to be able to figure out what this friction factor is. The only way we get it is by doing experiments. And if we did that now, even with all the computer power we have, we'd have to reproduce this graph, we'd have to do exactly the same thing, just by experiment. So that's why dimensional analysis, as it's referred to, is such an incredibly powerful tool, because it really allows us to do things without any kind of real analysis of the mechanics of the problem. We just need to have some kind of feel for what the important parameters are. And it goes back to the simplest expression that we made, is that we conjectured that these are the appropriate variables that describe behavior. We conjectured that the important behaviors we'd have is that the flow regime changes with Reynolds number, and therefore with Reynolds number the values of this, the pressures acting between upstream and downstream should change, and those pressure changes should be some way indicative of the frictional losses within the pipe. And so, armed only with that, we made the conjecture that these should be the parameters that would define our behavior. And indeed, the Moody charts define behaviors in terms of an appropriate Reynolds number and an appropriate roughness. And it's the roughness that really signals the transition to turbulence. So the last point I'll make as we head out of here is that the other thing that you notice is that we have some behavior in the laminar regime, which is kind of over here. Someone's phone, which is defined here. And as we increase the Reynolds number, we go into a secondary regime. So the boundary between wholly turbulent and laminar, so this is wholly turbulent beyond this dotted line. The characteristics of this are that all of these lines for the friction factors are constant. And so what it's saying is that this relative roughness on the boundaries of the tube has triggered this transition from laminar to turbulent flow as the velocity has gone faster. Now, once it's in that state, the friction factor doesn't change. And so it's actually useful for us, because if we know if we're in this wholly turbulent regime, we can just choose a straight number of this friction factor, which is what the elevation of this line is relative to this axis here. And so these represent the relative roughnesses, but these represent the magnitudes of the friction factors. So the important regimes are here where it's laminar, where the friction factor changes with the velocity directly. Here where it's turbulent, where the friction factor is constant. And of course, the value where you get transition from one to the other is indexed by the relative magnitude of the Reynolds number. And so the final parting shot to notice is that as you have very rough walls, then this transition to turbulent flow happens much earlier than if you have really smooth walls. Right? This Reynolds number here is very high. For a very smooth, infinitely smooth tube, it happens at a very big Reynolds number. But for a relatively rough walled tube, it happens at a relatively small Reynolds number. And so we'll use that in the coming sessions to be able to usefully use this expression to be able to figure out exactly how we solve for these pipe networks, which say something about how much fluid we can put along for a given amount of energy. Okay? Thank you very much. Okay.